So let's take a look at something like this. I want to determine the stability. Actually, you know what? I think we should actually we'll come back to the stability. Let's do what Erica said first. That's a good idea. We'll come back to the stability. Let's see. The problem with these ones is, well, actually, no. Oh, yeah. How do you get this again? Let's do one that's a little bit ugly. Sometimes they're not going to be nice. Yeah, I had a good example over here. Let me just grab it real quick. Yeah. Let's say we want to solve the following system of differential equations. We want to solve dx1 dt equal to 4x1 minus 9x2 and dx2 dt equal to x1 minus 4x2 with the initial condition of 2, 3. And you can write this like this, or you could say it as, you know, x1 of 0 is equal to 2, x2 of 0 is equal to 3. Are you guys more of like an xy kind of crowd in class, or are you x1, x2 in class? Does he kind of go back and forth?
He just did this yesterday. He did like x1, x2.
Okay. I mean, either way is fine. It really doesn't matter, but it's so this one is going to be a little bit uglier than the ones you've probably seen because our eigenvalues are going to be not super nice. So let's find the eigenvalues. So, and again, when I say solve, right, what it means is we want to find, you know, x1. So solve means find x1 of t and x2 of t. And what they're equal to. This is the whole process where we find the eigenvalues, find the eigenvectors, and then throw it all into the equation, and then we have to find the constants as well. So let's go ahead and do all that. Again, we've seen a lot of these already in here, so this one I am giving us is a little bit less nice. All right, so eigenvalues. Okay, is this the penny to throw away? It might be the penny to throw away. I won't throw it away, but I'll just keep it and use it again. And then I'll have to say I'll have to throw it away. So eigenvalues, we're going to do, well, that's interesting. Yeah. So the determinant of 4 minus lambda, -9, 1, -4 minus lambda. Okay, so let's see if we get this here, it's going to be 4 minus lambda times -4 minus lambda minus -9 times 1, which ends up being, let's see, lambda squared plus 4 lambda minus 4 lambda, those go away. So we're left with, let's see, a -4 times 4 is -16 plus 9, 0. So we've got a very unsatisfying lambda squared minus 7 equal to 0, which we could factor, or you could just bring the 7 over and solve either way. Either way, you're going to get lambda equal to plus or minus the square root of 7. So there is some good news here. If this was a classification question, we'd be done because our eigenvalues are opposite signs, one positive, one's negative. So we know that this means, even though this wasn't the question, we know this means that our equilibrium is a saddle. So 0, 0 is a saddle because the eigenvalues are opposite signs and real, right? They're real and opposite signs. But that's not what we were asked to do. We were asked to, you know, solve the system. So we've got our eigenvalues, which are not nice integers, kind of for the first time ever. Now we have to find the eigenvectors. So finding the eigenvectors, this is the time where I would probably choose to do it the other way. Here's what I mean. So usually, if you're James, you want to find eigenvectors by doing the whole, you know, or even if you're you want to do them either if you or me, you want to do it by solving A times your eigenvector equals your eigenvalue times your eigenvector. And that's usually the better way to go if your eigenvectors are nice integer values. But if they're not nice integer values, if they're a terrible square root, it's often a little easier to do it if you do it the other way. So instead of doing it this way, we're going to do it this way. Oops, that should be an X over there, sorry. We're going to do it this way instead, just to kind of point a couple things out. So here we're going to have our matrix. Let's write our matrix over here, just so we still have it on the page. 4, -9, 1, -4. And to solve this, we're just going to solve. All right, so we've got for lambda equal to the square root of 7. Let's call that lambda 1. We have our matrix A minus lambda times our eigenvalue, sorry. So 4 minus the square root of 7. And let's see, then we've got -9, and then we've got 1, and then we've got -4 minus the square root of 7. Times x1, x2 equals 0, 0. You could do that, or just to point out what we usually would have done, we could have done this versus 4, -9, 1, -4 times x1, x2 equal to the square root of 7 times x1, x2. Solving this is just a little bit less nice. You're going to get 4x1 minus 9x2 equals the square root of 7x1. It's not super terrible here. It's extra terrible if your eigenvalues are like 3 plus or minus the square root of 5, where you have the irrational part and the rational part. Here, this is okay, but doing it this way is better. We can pick either one of these equations, but look what happens when we do this. I'm going to pick the second equation, actually, so it looks a little nicer. Picking the second equation, I'm going to get 1 times x1 equals, minus plus -4 minus root 7 times x2 equal to 0. And that makes it really, really easy to solve for either x1 or x2. Specifically here, x1. We could say that x1 is equal to 4 plus root 7 times x2. So now the eigenvector we could write, and I will say your mileage will kind of vary on these ones. People get lots of different looking answers that are all equivalent, but it's really easy to make a different choice than someone here and see, and not easily be able to see that one's a multiple of the other. But here, if we do this, I'm going to let x2 equal 1 and x1 be 4 plus root 7. So my eigenvector is that. There are other good choices. This is the choice I made. Yeah. Question. Right. I'm doing it this way. Normal is not a good word, but right, but like they're both standard. I think a lot of classes often do it this way instead of doing it this way. In this class, we have certainly been doing it this first way the whole time up until today.
So would you like say that if you have like nice numbers, then that way don't.
Exactly what I would say and have been saying. So yeah, so do it this way if your eigenvalues are nice, meaning integers typically, and do it this way if your eigenvalues are not nice, meaning irrational. And I'll point out if your eigenvalues are complex and you have to, bless you, find the eigenvectors, there's actually a whole other thing you have to do that is more complicated than this. So this is really only if they're irrational over here. Okay. So something I wanted to say. Oh yeah, there is something really, really nice. So here's what's kind of awesome about, this is actually true for irrational, well, I should say, yeah, I'll just say this. For eigenvalues, if they're irrational, they come in conjugate pairs. So right, we have a plus root 7, we have a minus root 7. Or if there was something else, we'd have like a 3 plus or minus root 5. But what's great about this is their eigenvectors also come in conjugate pairs. So you don't have to do all the work to find the other eigenvector. You can say, okay, well, for lambda 2 equal to negative, we're going to do the work just so you can see it, but I'm going to tell you right now, for lambda 2 equal to negative root 7, we are going to be able to get to the second eigenvector being, well, just take that eigenvector and change all of the irrational parts to their opposite sign. So it should end up being 4 minus root 7, 1. Which is kind of great. So let's check though. So I do the work. Well, actually, you can almost get away without doing the work, because all we're going to do in our equation here is change all the minus root 7s to plus root 7s, because now we're subtracting negative root 7. So we're going to have 4 minus root 7, still a negative 9, still a 1, and a negative 4 minus root 7. Still times x1, x2 equal to 0, 0. And look, if we use the second equation again, because that's easier, I have a 1x1 plus a -4 plus root 7 times x2 equal to 0. And solving for x1, I've got x1 equal to +4 minus root 7 times x2. So letting x2 equal 1, oh yeah, x2 equals 1, x1 equals 4 minus root 7, which is exactly what we've got over here. So it's super nice. So if you have eigenvalues that are not complex, just regular conjugates like this, once you get one eigenvector, you automatically have the corresponding eigenvector for the other eigenvalue. It's great. So now we can write our solution, or I should say, now we can write our general solution because we have the eigenvalues and the eigenvectors. So general solution, usual thing, definitely should memorize. The general solution is going to be x1 of t, x2 of t, or x of t, y of t if you're using x's and y's, equal to c1e to the lambda 1 t times v1 plus c2e to the lambda 2 t times v2. I do think it's worth writing this down every time, just to at least until it really sticks inside your head that is what we've got. And then we're just going to write them down. So our general solution here is going to be, let's see. So I don't know what C1 and C2 are yet, but I know what everything else is. C1e to the lambda 1 was the square root of 7 times t times v1, which is 4 plus root 7, 1. And then C2e to the negative root 7t times 4 minus root 7, 1. And then if they haven't given you initial conditions, this is where you're done. You can't do anything else. If they're giving you initial conditions, and they typically have for most of your homework problems, the expectation is that you then use the initial conditions to find C1 and C2. So we're going to use the fact that, what did I write down here? x1 of 0 is equal to 2, and x2 of 0 is equal to 3 to find C1 and C2. Cool. So how ugly does this get? Oh, not that bad. So we're just going to do it, and it's really not too terrible. We're going to plug, well, at least it looks like it's not going to be too terrible. Let's see. So I'm plugging in 0 for t, which just means that the e parts go away. Right? That's all that's really going to happen. Is I'm plugging in 0 for t. These parts are both going to be 1. This is going to be 2, 3. No, 2, 3. Right? I'm plugging in t equal to 0, and that's going to equal c1 times 4 plus root 7, 1, plus c2 times 4 plus root 7. Sorry, 4 minus root 7. So we've got two equations. The easier equation, c1 plus c2 equals 3, and the less nice equation, c1 times 4 plus root 7 plus c2 times 4 minus root 7 equals 2. So write them down. Hopefully we can make some easy sense of them. This is where things probably are not going to be quite as nice. This is definitely a case where I probably wouldn't try to do elimination, right? Like it's not going to be easy to multiply this second thing by like -4 minus root 7 and add them together. This is definitely a case where we should solve the easier one for one of the variables and plug it back into the other one. Doesn't matter which one you pick. Let's say that C1 equals 3 minus C2. And then we'll substitute that back in for C1 in the first equation. So then we're going to get 2 equal to 3 minus C2 times 4 plus root 7 plus C2 times 4 minus root 7. And now it's really just some arithmetic. So let's see here, multiplying things out. We've got 3 times 4 is 12, 3 times root 7, minus 4c2, minus c2 times root 7, plus 4c2. That's a blessing at least. Those are going to cancel. Minus c2 times root 7. So the minus 4c2 plus 4c2 cancels out, adds to 0. And then I'm left with, let's see, I've got a 2 on the left equals 12 plus 3 root 7. And then I've got a minus c2 root 7 minus c2 root 7. So a minus 2c2 root 7. I'd probably bring that over to the left just because it's negative and I want to make it positive, but it doesn't really matter. So bring that to the left and you've got 2c2 root 7 equal to, bring the 2 to the right, so 12 minus 2 is 10 plus 3 root 7. Finally, divide by 2 root 7, so c2 equals 10 plus 3 root 7 divided by 2 root 7. And then if you're looking at solutions, it's pretty standard to rationalize the denominator here. So I'd multiply the top and bottom by root 7 to get something not particularly nice looking. We're going to get c2 equal to 10 times root 7 plus 3 times 7 is 21 over 2 times 7, which is 14. Or, yeah.
If you add yeah, when you added that to the place, what happened to that?
I subtracted it. 12 minus 2 gave me the.
Oh, you did on that.
Yep, yeah. So yeah, gross. And then our C1 is 3 minus C2. So that's going to be 3 minus C2, which I'm going to write as 42/14 minus all this grossness. Now check this out. It's kind of cool. You're going to get the same thing, but it's going to be the conjugate. If you subtract this, and I know I've run out of room, so let's give ourselves a whole piece here, right? If you subtract this, you're going to get paper. You're going to get C1 equal to 42 minus 10 root 7 minus 21, because that distributes over 14, which ends up being negative 10 root 7 plus, plus 21 over 14. So C1 and C2 are conjugates. Now I've not written them in the way that it makes it more obvious that they're conjugates. I probably should have. I probably should have written them as C1 equal to 21 minus 10 root 7 over 14, and C2 equal to 21 plus 10 root 7 over 14. And I can't say with 100% certainty because I haven't explored this super a lot, but my bet would be that just like all the other things in the situation come in conjugate pairs, you're constant. I feel like that doesn't seem, it feels like a coincidence to me. I'm not 100% sure. I would really love to be able to say that these constants also come in conjugate pairs, but I feel like that might be a reach. I would say it's something to look out for. Again, hopefully most of the time your coefficients are not super ugly like this, so you would just not have to worry about it. But if they are, so our final solution looks like x1 of t, x2 of t equals C1, 21 minus 10 root 7, or 14, times e to the lambda 1, which was root 7t, times v1, which was 4 plus root 7, 1, plus c2, 21 plus 10 root 7, over 14, times e to the lambda 2t, that's negative root 7 times t, times v2, which was 4 minus root 7, 1. Pretty heinous to write out, but again, it's the same sort of steps the whole time. You're just finding the eigenvalues, finding the eigenvectors, finding those constants, and then throwing it all into this formula. The last thing I'll mention here with this particular example is that often in your homework, they're asking you to write x1 and x2 separate. In your homework, if you were actually trying to write this, it would be, again, kind of gross. The x1 of t would equal this 21 minus 10 root 7 over 14 times e to the square root of 7 times t times 4 plus root 7 plus 21 plus 10 root 7. That's a 21 plus 10 root 7 over 14 times e to the negative root 7t times 4 minus root 7. And then the same sort of thing for the other one, which I guess I could write down. X2 of t is not quite as gross. X2 of t is going to be 21 minus 10 root 7 of 14 times e to the root 7t times 1 plus 21 plus 10 root 7 over 14 times e to the negative root 7t times 1. So not quite as bad. Something to be careful about here, if you have radicals as your eigenvalues, make sure that that t is not in the radical, right? That is the square root of 7, end of story, times t. That is the negative square root of 7, end of story, times t. You can write the t in front if that's easier to keep track of. Okay. So, good question. So I would say, this, well, let me answer a different question first. So this particular solution here would show you the graph on the phase plane that starts at the point 2, 3. So in fact, to answer your question, let's actually look at it. Because honestly, that's the best thing to do, is to see what's actually happening here. Maybe. Where are you at? Yeah. So all we're going to do is we're going to take our phase plane plotter. And again, I do recommend this one. It's probably the easiest one to access. And write in our set of differential equations, which were, back to remind ourselves, dx1 dt equal to 4x1 minus 9x2. So it's going to be 4 times x minus 9 times y, right? Because we're using x for x1, y for y2. And then the next one's going to be dx2 dt equals x1 minus 4x2, or x minus 4 times y. And then we will graph it. And so if we actually start at the point 2, 3, which is what our initial conditions were, so we go over 2 and up 3. Find here from this vantage point. Does that look right? 2, 3. We start there. That line is actually kind of what is represented by our solution, right? This solution says that if you pick any value, oh, sorry, you can't see the endpoint yet. So if you pick any value of t in this particular solution here, you're getting points on that line. Now, t isn't represented there, right? So I should point out that at this point we started at here for this particular solution that we have, this point here at 2, 3, that's at time equals 0. And then if you plugged in time equals 1, you would move further in this direction. Now, I don't know exactly what point it would be, because actually plugging in t equal to 1 into this equation would be super gross. But if you plugged in t equal to 1, you would get, something like this times e to the root 7 times 4 plus root 7 plus this times e to the negative root 7 times 4 minus root 7, and you would get some x coordinate. And if you plugged in t equals 1, here you would get some y coordinate, and that xy coordinate would be wherever you were along down the path in the direction that the arrows are moving. So you start here at t equals 0, and then you move along in this direction. Now, that's gross. You can also actually plot each of these things individually, which is terrible. We don't usually do that super, that's what I'm looking for. We don't do that with a lot of precision. Like if I was actually asked to, graph these things each individually versus time, I wouldn't think super hard about actually trying to make it, especially if this is really gross. But if you actually said, okay, I want to plot, x1 versus time, I would see, what would I see? I would see that looks terrible, but that eventually things are going to get really, really big because, well, one, it's a saddle, right? We know it's a saddle, we know it's unstable, so things don't go to 0, they go off to infinity. They're kind of your only choices. This one might have a little dip at first because maybe this one's going to make it go down a little bit at first as time gets a little bit bigger, but eventually what's going to happen is you're going to get larger and larger and larger. If you plug in 0 for t, oh, well, we know where we start if we plug in 0 for t. What's our x value if we plug in, what's our x1 value if we plug in 0 for t? Let me go back and help you out. What's our x value if we plug in 0 for t? 2. And what's our y value plugging 0 for t? So if you're going to graph this, you would start up here at 2. And then I don't exactly know what it'll look like, but it might do something kind of like that. And in a similar way, if we start at 3 for y, I don't know exactly what's happening in the middle. Maybe it just starts growing right off the bat. but it might dip down a little bit first and then eventually get larger and larger and larger. I don't actually know. If we look back at our phase plane, so if I start here, interesting. No. Ooh, my graphs might be wrong. That's okay, but let me talk about why my graphs might be wrong. So, oh yeah, because I didn't think about that. Interesting. Sorry, I have to think now for a second. Why am I wrong? So let me ask you: if we start here and we go and we follow the direction of the arrows, are my x values getting really, really positively big or really, really negatively big? Right, I'm going off that way. And if the same question for y, my y value is getting really, really positively big or really, really negatively big? Well, actually, it's not super clear for my graph, right? Like they look like maybe I'm just going to 0, but I think if we zoom out, let's try and make things a little bigger here just to kind of see. Hopefully this works out all right. We'll see. Might be terrible. You never know. This graph the same thing? Yeah. Okay. Sure. We start up here. It's not super helpful. It looks like the eventually might go down, 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 further and further, further. Now I'm really happy. Now that's what should happen. Yeah. So if we look back at our equation for a second, if we think about what's happening here, 10 times root. Oh yeah, yeah. This number is negative. I just hadn't noticed that before. So since this number is negative, and this part's the part that's growing, this is good as t gets larger and larger and larger, this part's going to get very, 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 very negative. And so our x values are negative. Same, maybe not the same deal here. This part is no, this part's also negative, so same deal here. So really my graphs probably should have done something more like this, actually. Like wah, 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 like that. Probably something more like that. So back to your question, Erica, which is what does the general solution represent? The general solution, it's not very nice, really, but the general solution represents kind of the whole phase plane. So the whole, like, basically you're saying, well, right, if you start, depending on where you start, anywhere in here, right, the line you start at, that's a solution. This line you start at, that's a solution. So there's lots of different solutions depending on where you're starting at. But they would conform to how this sort of graph looks like. And we've got this whole satellite relation nature thing here. Oh yeah, that's yeah. And so we've definitely got a saddle. We're definitely moving towards the eigenlines, which would be not very nice lines here. Right, our eigenlines, we could find them, but they're just the lines that go along the eigenvectors. So the eigenlines would be something like over 1 and up 4 plus root 7. And this is actually the one that we would go in the direction of because that's the eigenline that's the positive, positive eigenvalue. So whatever this eigenvector, eigenline looked like, which is a lot more up than it is, sorry, a lot more over than it is up, right? It's a lot of over, like between 6 and 7-ish, not very much up, which makes sense, right? If we look back at our graph, that the line we seem to be getting closer and closer to looks like there's a lot of over and not a lot of up if we're thinking about going in like that direction there. So that seems reasonable-ish. Other questions about this one? I'm not looking at you guys with this one. Looking over here too. So finding general solutions, this one's kind of probably the worst case scenario. It could be a little bit worse, like you could have like a 3 plus or minus root 5 kind of deal. But I feel like, at least so far, irrational eigenvalues are about as bad as it gets, is actually having to find the solution. And they might not even be that bad. You might always be just with a nice kind of everything's nice and great eigenvalues. So let me ask you all to kind of, let's do one more. I'm gonna have you all work on it. So let me come up with something that's not super awful here. Why don't you all try finding the solutions to, oh, I've got. Let's see. One second, I've got a note. Help me do this. Yeah, all right. Sure, why don't you try finding this one? The solution. Find the general solution. Can you see what I'm writing? Yes. To the system, dx dt is equal to, do that. Sure. 3x. Give me a moment to make up the numbers here. dy dt equals, let me see here. So 3, want to negative 1 times y, 2, and then I want 3, negative 3, it's 5, sure. So I want sure, a 5x here and a minus y here as well. Not going to work out, I think so. Let me double check. Sure. 2, yep, and negative 3. Nope, I want that to be a plus. There we go. Okay, so find the eigenvalues. Give you a couple minutes. I think you should. No, they're making me worried. I'm pretty sure.
Is it negative? In the first equation or positive?
It's a positive.
Oh.
Sorry, I
okay,
did
my
change.
bad.
I did change it midstream there.
Oh, okay.
Yeah, so just so everyone's on the same page. Sorry about that. That's a 3x plus 1y, and there's a 5x minus 1y. Sorry about that. Yeah, otherwise, I think the eigenvalues are not so nice. No, they are nice. If it were a minus y there, I think they would turn out to be not very nice. Found the eigenvalues, which should be 4 and negative 2. Go ahead and start finding the eigenvectors. What's the sun coming out? fine. Yeah, I'll give you guys initial conditions as well. Now, I will tell you, if someone gives you initial conditions where it's not time equals 0, it's usually really terrible. So almost always it's gonna be time equals 0. So let's say our initial conditions are x1 of 0 equals, I'm just gonna make something up, it might turn out terrible, such as life. x2 of 0 equals -2. It would be a lot because you'd have the e. I mean, it wouldn't be a lot worse. It would just not be 30 because you have that e to the whatever part, and so then that would. Honestly, that was there's kind of a way to get around it, but it's not really what it's for because you can.
If T wasn't 0, we still have to put in T.
Yeah, so if T wasn't 0, then you would, like, if T was 1, for example, then in your general solution, or when you're trying to find C1 and C2, you would have whatever equal to, C1 e to the lambda 1 times 1, so that e to the whatever would still be there. Whereas when it's e to the 0, it's just. So here's what I want to point out. You don't need both equations. You don't really need the x to the y, y equals -5x. Then you can say x is 1, y is -5. Now, what should be true is no matter which equation you use, it should be the same. So what I'm going to here is if you add y over here, so that's a y on x. So we should do but really almost only ever need one of the equations, so you don't need to write that one. All right, I think people are pretty close to being done and have done most of the work. Let's just talk about so everyone, make sure everyone at home is on the same page too. So eigenvalues, pretty straightforward to find. You can either do it the usual way, or you can also think about the trace determinant method, where the trace is 3 plus -1, which is 2. The determinant is -3 minus 5, which is -8. And then your equation is lambda squared minus the trace times lambda plus the determinant of 0, which is the same as this. Either way, it factors, you get lambda -4 times lambda plus 2 equal to 0. And so you've got 4 and -2 as eigenvalues. Eigenvectors, we are just solving this equation. Again, this is the way I usually do it. The eigenvectors are nice, or if the eigenvalues are nice. So nice eigenvalues. I'm always just using the first equation unless there's a really strong reason to use the second equation instead. This only really comes up if your eigenvalues are not nice. If they're nice, either equation is going to be fine. You could totally use the second equation though, right? Like there's no particular reason to use the first one. If we use the second one here, you'd have 5x minus y equal to 4y, which would then give you 5x equal to 5y, which would give you x equal to y. So you're getting the eigenvector of 1, 1. And that should be the same eigenvector you got if you use the first equation. Here, same idea. If I use the first equation, I have 3x plus y equal to negative 2x. Subtracting 3x from both sides, y equals negative 5x. Letting x equal 1, I get x is 1 and y is negative 5. So that's my first eigenvector. My second eigenvector. Either equation should get you there, but you really, really almost never need both. The only times you ever need the second equation is the first one gives you like x1 equals x1 or y equals y, right? That doesn't tell you anything, and then you have to use the other equation. But other than that, you only ever need one of them. For the initial condition, we're just gonna, well, in fact, let's write the general solution. The general solution is now just throwing it all into this formula. It's the same stuff every time. I used x's and y's, sorry, not x1. So x, y equals c1 to, let's see, my lambda 1 I said was 4 times v1, which is 1, 4t, sorry, don't forget the t is important, plus c2 to the lambda 2, which is negative 2t times v2. Your answers might look slightly different than other people's. Maybe your eigenvector was negative 1, positive 5. That's totally fine. Maybe this eigenvector was negative 1, negative 1. Maybe you've written them in the opposite order. But as long as that eigenvalue goes with that eigenvector and that eigenvalue goes with that eigenvector, your answer is as close to the same as it needs to be. So then, I forgot my initial conditions. I just threw them away right there. X1 is 0. Oh, I used x1 and x2, of course. Or what I should have written is x of 0 is 6 and y of 0 is negative 2, because I was using x and y. But I think you all know. Yes, you know what we're doing. Okay, so we're going to plug in t equals 0, x equals 6, y equals negative 2, right? Right. So we're going to get 6 negative 2 equal to c1 times 1, 1 plus c2 times 1 negative 5. So let's see, I've got 6 equal to c1 plus c2. I've got negative 2 equal to c1 minus 5c2. Some people do this a different way, just to point out. Some people do this thing where you actually write this as a matrix equation and then find the inverse of this matrix and multiply both sides by the inverse. That's a valid way of doing it, but unless your professor really wants you to do it that way, I don't think I don't know, it's nice. It's kind of, in some ways, less work because the determinant of a 2 by 2 matrix or the inverse of a 2 by 2 is always straightforward to find. But it's just one more thing you have to remember. So I would say we shouldn't talk about that unless you guys are like, he wants us to do it this way. We should talk about it. But solving this is not too hard. I would probably do, instead of a substitution like last time, I would probably use the elimination method and say, oh, I'm going to take my first equation and subtract my second equation to eliminate the C1. 6 minus minus 2 is 8. C1 minus C1 is 0. C2 minus minus 5 C2 is 6C2. So I end up getting 8 over 6, which is 4 over 3 equal to C2. And then you can plug that back into either equation. I'd probably plug it back into the first one and say, okay, so then 6 equals C1 plus 4/3. So 6 minus 4/3 is equal to C1, and 6 is 18/3. So we have 14/3 equal to C1. And then we should go and write our final particular solution, right? It's not usually enough to be like, okay, I'm done. You have to go back and actually write that. And let's write it out in the kind of, I think your Weber problems are usually writing x and y separately. I don't love that, but it's fine. So I would write x of t equals C1, so 14/3 times e to the 4t times 1 plus C2, which is 4/3 times e to the negative 2t times 1. And then y of t would look like same deal or similar deal. 14/3 e to the 4t times 1. Let's do it this way. So I know I'm going to plug in a 14/3 here and it's going to multiply by -5. So -5 times 14 is -70. So I'm going to have a minus 70/3 times e to the negative 2t. What kind of stability did this have? Was my origin a sink, a source, or a saddle? Saddle. Definitely saddle because our eigenvalues are opposite sides again. This one would be a little bit easier to graph the individual pieces for, like if you wanted to graph X versus time and Y versus time, but we know when it's a saddle, everything is divergent, right? So either you're going up to infinity or down to negative. Just kind of depends. Here, we're definitely going to be going up to infinity because this part's going to dominate. Again, the one with the positive eigenvalue is the one that dominates. So this is the behavior that's going to actually matter. This, as time goes on, is just going to go to zero because you're going to get e to the negative bigger and bigger and bigger number. So this is going to look something like, and again, this is where I might actually use Desmos to graph it because trying to type that in Desmos is not super terrible. If you actually just want to see what it looks like for a second. So we have, I wonder if I just, sure, x of t, I don't really care. We'll see how this goes. Equals 14 thirds e to the 4t. Do you care if I use t? You do not care. Great. Plus 4 thirds e to the negative 2t. Well, it doesn't look right, does it? Well, it doesn't look right to me. So it's probably thinking that my x is actually my x. So I should probably be not so literal about it and maybe just use y instead of x to see what the graph looks like. That looks more reasonable. It doesn't look very nice, but if we actually like zoom in here, we can see, oh, look, our initial condition right there is 6, as it should have been. And so if we cut off the part that kind of maybe doesn't seem like we would have time being negative, so if we do this, then we just get that part there, which again, not super nice to look at because it's such a steep exponential function, but that's the idea here. And then we could look at the other one. It have a similar-ish kind of shape. It doesn't look like, it just looks like it's kind of going up into the left, up to the right. Cool. It might, there's probably some tiny little dip in the beginning that you can't actually see because of how big things are, but that's kind of it. Questions? It's kind of the same thing a lot, right? At least this homework, I feel like it's a lot of just, the questions are either find the solutions to this equation with these initial conditions, or the other half of the questions are take this system and tell me what my stability looks like. It's kind of, there's a couple other types of things, but for the most part, those are the questions on this homework assignment. So let's actually look at the other type of thing, because I do think we should talk about it a little bit more. So let's look at this example. I want to classify the stability of the equilibrium equilibrium 0, 0 for the following matrix. And I also say, additionally, if it's a spiral, tell me the direction it's spiraling. Spiral, tell me if it's clockwise or counterclockwise. Which definitely all of your spiral questions on your homework ask you about. So, couple ways to do this. You can either use trace determinant, or you can do it the other way. Yeah, let's use trace determinant. So the trace here is 1 plus -6, which is -5. The determinant here is 1 times -6 minus 5 times -13, which is going to be -6 plus 65, which is 59. Cool. Not cool. 59 is kind of too big, I feel like, but oh well. So here's what our equation always ends up being. Our equation is lambda squared minus the trace times lambda plus the determinant equal to 0. You would also get there the same way if you did the other thing, right? If you did this, 1 minus lambda, 5, -13, -6 minus lambda, and the determinant of that set equal to 0, you get to the same spot. So you might wonder, why is he asking me to do this other thing when we've got this one way of doing it that works all the time? The reason is because eventually, I know I keep saying eventually, we're going to talk about how you can just look at the trace and determinant and not write this whole equation and be like, oh, I can see that it's gonna be a saddle, or I can see it's gonna be a spiral, or a node, or whatever. Right, so I would say you should definitely conform to whichever way your teacher wants you to do it. But the thing I would say is sometimes we look at things later on, especially when we start looking at nonlinear systems of differential equations, where you can't exactly have the values in the matrix, but you can have enough information in the matrix to see if the trace and or determinant would be positive or negative, and often that's enough information to classify whether we have stability or instability. So that's kind of why I'm actually, I know it's been a lot of talking about this thing, saying eventually we're going to do a thing with it, and then be like, but we haven't yet. Eventually we're going to do a thing with it that actually is going to be like, we couldn't do it another way. So that's why I keep saying it. It's good to see both ways, but if you are more comfortable with this, you should definitely do this. Just know that they get you to the same place. So in either case, we end up with the quadratic formula or the quadratic equation, lambda squared plus 5 lambda plus 59 equal to 0. And then we want to solve that. It definitely doesn't look like it factors. So we are in a lambda equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Which I will point out is always going to be the trace plus or minus the square root of the trace squared minus 4 times the determinant all over 2. That always, so that is a nice way of doing it. Also, you don't have to go through the whole thinking about the formula every time, but whatever. In either event, this is going to be imaginary or complex. So we get lambda equal to negative 5 plus or minus the square root of, let's see, 25 minus 4 times 59 is, thank you, and 25 minus that is going to be negative 211 all over 2. And at this point, I don't really care what the numbers are. Some people might decide to rewrite this as, I don't think you need to, but you can write this as negative 5 halves plus or minus I times the square root of 211. People do that. The only thing we really need to see here, oh, sorry, I square root of 211 over 2. The reason you might break this up into 2 pieces is to make it slightly easier to see that my real part here is negative. Because the real part being negative tells us whether we are stable or unstable. And the being negative tells us specifically which we're stable. Just like both eigenvalues being negative, the real tells us it's stable. So that tells us that we have a stable, and the fact that it's imaginary tells us it's going to be a spiral. That's the way I kind of think about it anyways. Like the imaginary part is like, oh, spiral, and then the real part's like stable or unstable. So we have a stable spiral, stable or inward spiral. And the other question we have to answer is, which way is it spiraling? I have no idea. So even though there is a way to look at the matrix, and I do believe if it's positive up here, that means you have if it's positive in the upper right corner, when is the spiral? I believe that means it's clockwise. And I kind of, I used to be like, that's great. Just like look at it, you know. But what I've realized is, if someone's actually testing you on this, they're not going to want you to be like, well, I looked at the matrix and I learned a thing somewhere in a book, and I know it's clockwise. What you probably should do on an exam anyways is draw a picture to indicate how you figured it out. So here's what I would suggest. Plot just a few points in the phase plane. Maybe sometimes all you need is 1. Now, I think plotting 4 is probably more likely, but let's say here's our phase plane, and I'm typically going to look at the points 1, 1, 1, negative 1, negative 1, negative 1, and 1, 1. And I'm going to look back at my differential equation. So my differential equation, which I didn't actually write down, was dx dt equal to x plus 5y, and dy dt equal to negative 13x minus 6y. What we're going to do is we're going to plug in each of those possible points to these differential equations. So at 1, 1, dx dt is equal to 1 plus 5, and dy dt is equal to negative 13 minus 6, which is negative 19. So here's what we're going to do. Sorry, we're going to want to see things first of all. We're going to, at the point 1, 1, we're going to go 6 to the right and 19 down. but we're not really going to go 6 to the right or anything. We're going to go in that direction, meaning we're going to go kind of what I would say is 3 times as much down as we are going over. So I'm going to go a little over and more down. So I'm kind of pointing that way. That's what I would say. And just from that, I could probably convincingly say we're going clockwise. Now, one second, okay. So let me say 2 more things before I get to you. So we might test one more point. Let's say we want to test 1 negative 1 just to be absolutely sure. We test 1 negative 1, your dx dt is 1 minus 5, your dy dt is negative 13 plus 6, which is negative 7. So we're going left and down. Yeah, I'm pretty convinced. And we're going more down than left, so we're going kind of like that. Looking pretty clockwise to me. Now, the other thing I'll say is let's pretend just for a second. I can make one. Well, let's pretend we did this and our point was at the point 1, 1. Let's say the point was pointing maybe something like, let's say it was pointing like this. And maybe drawn that a little too ambiguously there. But what I want to say about that is, if you're not sure, what you do is you can draw the line from the origin to your point, which I didn't do a very good job of there. But what I want to show you is that the thing I've drawn is just on this side of that, on the going counterclockwise direction. So basically, whatever line would take you back to the origin from your point, if you're on the this side of it, you're going counterclockwise. If you're on this side of it, you're going clockwise. Kind of funky. But like, if you think about, like, so for example, if you had a point like here and your vector was pointing in a not lovely direction, but maybe like not, it's like, I feel like I'm giving away the end. Let's say we're pointing like that way. It's maybe not super clear if you're going clockwise or counterclockwise. But if you draw this line back to the origin, you're like, okay, well, I'm going to be going that way. You're going to be going counterclockwise, which again might be a little not intuitive, which is why we typically draw a few more points than just one. Now, what I will also say, and then I'll pick it to Erica, is that you can certainly, I think you should draw it every time so the person grading your work can see that they know what you're doing, like on the test. But it's worth recognizing that if it's a spiral, it is indeed true that, so when you have a spiral, you might want to see what I'm writing. So when you have a spiral, there are 2 things that are going to be true. Thing 1, in this matrix, B and C will always be opposite signs. And 2, if B is positive, then you have clockwise. And if B is negative, then you have counterclockwise. So what I would say is you should still draw it, but then you can look back at your matrix and be like, oh, well, I know that B is positive, so I know it's supposed to be clockwise. Or I know that B is negative, so I know it's supposed to be counterclockwise. So that's probably a good way of doing it. It's kind of like when they asked you back in 17A, maybe to do like the limit definition of the derivative. And you're like, okay, well, I know the derivative is actually going to be this. I still have to show my work using the limit definition, but I know what the answer should look like. Same kind of idea here. We should show the work to see which way it's really going, but we kind of already know what the answer is going to look like. All right, Erica, what did you have to say?
That point you just saying that we couldn't just lie that
Right. I think it is, it's not that it's not correct. It's just that it's not showing really anything. Like, it's just, you just memorize the facts. And I don't think if your teacher hasn't talked about it in class, then I'd be like, well, where did they get this from? And so I wouldn't rely on that on an exam because it's just, you're not showing that you know what's really happening, I feel like. Yeah. It is interesting, I think, that if you have a spiral, meaning if your eigenvalues are negative, it had to have been true that B and C are opposite signs. And seems weird, right? Like, so what we're really saying is to have gotten imaginary eigenvalues, these can't be the same sign. That's interesting. I don't want to figure out why that's true, but it's true. Anyway, let's look at another thing here. So, okay, where'd you go? So yeah, let's go ahead and say the thing. So here's what's something that's kind of cool. I think. So we've talked about this trace determinant method a couple times, and this might be a place where you'd be like, okay, James, well, whatever. But let's show this one more time, just so that you can be maybe more convinced. So if our matrix is just a general A, B, C, D 2x2 matrix, then we can find the solutions to this characteristic polynomial, finding the eigenvalues by doing the determinant of A minus lambda I equals 0. That's going to be the determinant of A minus lambda, B, C, D minus lambda. And that's going to be A minus lambda times D minus lambda minus B times C. Which if we multiply this out, let's see what we get. We're going to get, oh, that's equal to 0, sorry. So we're going to get lambda squared. We're going to get minus lambda times D minus lambda times A. So minus A lambda minus D lambda. And we're going to get plus AD minus BC. Or written another way, check this out. Lambda squared minus A plus D times lambda plus AD minus BC. Or in other words, lambda squared minus the trace times lambda plus the determinant. So hopefully you extra believe me now when I said this is another way again. It's really the same thing. But what's cool about this is then if we find the solution or the eigenvalue just using the quadratic formula, we can write the quadratic formula as, or lambda as, the negative of the negative trace here. So the trace plus or minus the square root of, and I know I did this last time. But now you can classify things very, very easily by saying the following. So, a couple things to note here. So the lambdas, the eigenvalues, are going to be real if the inside of that square root is not negative. So if tau squared minus 4 lambda is greater, sorry, minus 4 delta is greater than 0. Or as some books like to write, and there's actually a nice picture of this in your textbook, which we're going to see in a minute here. The way we're actually going to think of this is if delta, the determinant, is less than 1/4 the trace squared. All I did was bring the determinant over to the other side and divide it by. Okay. On the other hand, the eigenvalues are going to be complex if that thing is not true. If, oh, and I should have said greater than or equal to, I suppose, but we don't really actually, the equal to part, we don't care so much about, so I'm just going to say greater than. If the opposite's true, if tau squared minus 4 times the determinant is less than 0. Or in other words, if the determinant is bigger than 1/4 tau squared. So what we're saying here is that you can totally just look at the determinant of the trace and automatically determine if you have complex eigenvalues, meaning spirals, or real eigenvalues, meaning nodes or sinks. Or I mean, nodes are not sinks, sources, or what's the other one with reals? Sink, source, oh, saddles. So we know, right, if the eigenvalues are real, every time, that means you know you're going to have a sink, a source, or a saddle. Whereas if the eigenvalues are complex, you know you're going to have a spiral, an outward spiral, an inward spiral, or a neutral spiral, which we haven't had an example of yet. So now here's what's kind of neat about this. And I'll just show you, well, I'll draw the picture for you. So what people like to do is they like to say, well, we can kind of plot sorry, what do we got here? Determinant versus trace, and talk about what solutions look like based on what your determinant and trace are. So the thing that kind of matters is this determinant being equal to 1/4 the trace squared. So here's that parabola where the determinant is equal to 1/4 the trace squared. Now check this out. It's kind of cool. I promise you, it's kind of cool. Up here, where the determinant is bigger than 1/4 the trace squared, we have spirals. So up here is spiral land. And specifically, if the trace is positive, meaning if the real part of our eigenvalue is positive, we have unstable spirals. So over here, unstable spirals. And if the trace is negative, meaning the real part's negative, we have stable spirals. And then below this parabola, we have stability. So over here, where we have, right, where this is, oh gosh, words, James, where this part here is positive, then you're going to have real eigenvalues. And if this part's positive, then you're going to have, well, a couple different things can happen. If you're up here where the determinant is positive, you're going to have unstable nodes. Or over here, a stable node. And then down here, where the determinant's negative, saddle land. And here's what I think is kind of worth seeing. I want you all to see this because I think it's cool. If your determinant's negative, in fact, let's just write it over here. So our eigenvalues look like this. So here's the deal. If your determinant's negative, then tau squared minus 4 times the determinant, that just got bigger, right? If your determinant's negative, -4 times the negative number is positive, tau squared plus a positive number is bigger than tau squared, right? If your determinant is negative. Everyone cool with that? Everyone cool with that? Okay, now check this out. I have a number that's bigger than tau squared, and I'm taking the square root of it. So the square root of this, tau squared minus 4 delta, where delta is negative, is bigger than the square root of tau squared. Just tau. Technically, it's the opposite value of tau. Now, if you take tau and you add tau, assuming they're both positive, the whole thing's positive. If you take tau and you subtract, if you take tau and you add a number bigger than tau, positive. If you take tau and you subtract a number bigger than tau, it's going to be negative. So in this case, where the determinant is negative, you always end up getting something plus a number bigger than it and something minus a number bigger than it, meaning you're always going to get one positive and one negative. And that's why you always get a saddle when the determinant's negative, because you're always adding something bigger than this thing and subtracting something bigger than this thing. On the other hand, if this value in here is positive, but it's smaller than tau, then they're both going to be the same sign, because you're adding something that's smaller than it and you're subtracting something that's smaller than it. So if it was already positive, both things are going to be positive. If it was already negative, both things are going to be negative. So here's the picture in your book that I think is worth bookmarking. On page, I don't know, I bookmarked it here. And I find it, it's literally, I can't just turn to it. Okay. It's on page 650. It's in section 10.2 of your textbook. It's this picture right here, which shows you all of the stuff. So we have, right, so above this line, determinant of A equal to 1/4 the trace of A squared, Above this line, you have spirals. Below this curve, sorry, not line, curve. Below this curve, you have nodes, and then below the axis here, you have saddles. So what this does for us is says all you really have to do is find the value of the trace, the value of the determinant. And if your determinant's positive, you have to compare sizes. But that's, you could get away with just doing that. Meaning, for example, if we had something like a matrix representing a system that looks something like, I don't know, I'm gonna make something up, hopefully it turns out neat. 4, 3, 2, 8. I could just find the determinant and the trace and then use that graph. So my determinant of A, which we usually write as delta, is going to be 32 minus 6, which is 26, which is positive. So we know it's not a saddle. Greater than 0, not a saddle. Okay, and then my trace is 4 plus 8, which is 12. So then I have to see, okay, well, is my trace squared minus 4 times the determinant positive or negative? I think it's negative. Let's see. Well, oh no, I don't know. I was wrong. I was thinking I forgot to square it. So that's going to be 12 squared minus 4 times 26, which is 144, minus 104, which is 40, which is positive. So that means the inside. So honest, like I have a hard time being like, is delta bigger than 1/4 the trace squared, or is delta small? That's usually not the way I actually really think about it. But in this case, our determinant delta, which was 12. Nope, gosh, brain, 26 versus 1/4 12 squared, which is 36. So here we're in the case where delta is under that thing. So we're in the not spiral land. We're in the node land. We are right here. Honestly, what I was really doing though, was I'm thinking about the inside of the square root thing right there. If the inside of the square root thing is positive, then I know my eigenvalues are real. The inside of the square root thing is negative, I know that they're not real.
So like how you know that if the determinant is negative, then it's a saddle. Is there any criteria for like the trace being negative?
Yes. So if the trace is negative, we don't know if we have spirals or nodes, but we definitely know that we have stability. So the trace being negative means you have stability. Either a stable, well, I should say, if we don't have a saddle, right? Because if your determinant is negative, you're done. Saddle doesn't matter. But if your determinant is positive, then you can look at the trace and say, okay, well, if the trace is negative, you have stability. You have a stable either node or spiral. You still have to figure out which it is based on this. If your trace is positive, you have instability. Again, either node or spiral, which totally corresponds to this whole graphical idea here, right? If we're on the right-hand side, where the trace is positive, oh yeah, look, it's unstable node, unstable spiral. If you're on the left-hand side, where the trace is negative, oh, you have a stable node or a stable spiral. Unless the determinant happened to be negative, and then you didn't even think about any of that because if your determinant is negative, you had a saddle to begin with. So I would say if you're doing this trace determinant thing, look at the determinant first and ask yourself, is the determinant negative? If yes, saddle. If no, then we have to do more. So in this case, our answer was no. Our determinant wasn't negative, it was positive, right? Our determinant was 26. Our trace being positive means we are definitely unstable, but then we still have to determine if it's a unstable spiral or an unstable node. And the way you determine that is by looking at whether or not this thing is positive or negative. Or, right, you could also look at this, right? This here is spiral. This here is node. Right, so this is the thing, right? Usually people look at this like we could just find the eigenvalues. which might feel easier. The reason we're really talking about this is because we're gonna get to a juncture at some point, probably, where we can't actually find the eigenvalues. But we can still know enough about the matrix to determine if the trace is positive or negative, determine positive. So that's kind of why we're talking about this. But you're totally right. It would probably make a lot more sense to just say, hey, James, I've got my trace, or even just say, I've got my trace, but I've got my determinant, and let's find the eigenvalues using the trace determinant method. My eigenvalues are going to be, I always have a hard time remembering if it's negative. It's going to be 12, the trace plus or minus the square root of the trace squared, minus 4 times the determinant, all over 2. And now it's pretty easy for me to see, oh, that's going to be 12 plus or minus the square root of 144 minus 104, all over 2. We know it's not a saddle because we already know the determinant's positive. So are my eigenvalues real or imaginary? Am I taking the square root of a negative or not? No. So since I have a square root of 40, right, it's not square root of a negative number, my eigenvalues are definitely real. And they can't be opposite signs. They can't be opposite signs because we already know it's not a saddle. And to be a saddle, the eigenvalues have to be one positive, one negative. So, since they can't be opposite signs, we know they're both real. Are they both positive or are they both negative? They're both positive. Sometimes it's easier, like here it's pretty easy to say to yourself, oh, 12 plus root 40, obviously positive. 12 minus root 40, also fairly easy to say that's positive. It's harder when this number is closer to that number. So that's why I was trying to use a different way of just saying, well, like I can tell they're both positive because they can't be opposite signs. They're definitely not negative, so they have to both be positive. Real, both positive. And that means that we have an unstable node. So there's lots of ways to attack this kind of thing. What I should really say is do what's best for you.
And just clarify, because if it was negative, then that means
Correct. Yes. And if it was a positive number here, it'd be an unstable spiral because the real part would be positive. So the trace definitely does determine whether it's stable or unstable, if it's a spiral or a node. If it's a saddle, it's just unstable. Okay, I should stop talking. It's 3:01.